Now here's a demonstration of white noise. Well, I'm not going to show you what this produces, but I've given you a couple of MATLAB instructions here. And you can simply run these by yourself and see what they produce. Essentially, you will hear these signals. I'm defining a sinusoidal signal here, and this command actually plays it out. Okay, it normalizes it in range from -1 to 1, and then it plays it out. Since this is a single sinusoidal on one single frequency, this will be just a single tone. Just try it out, okay? And as a variation here, I have a function or a signal, let's say, which has which involves two frequencies, okay? So this one, you can play with these two numbers to have different combinations, and you can listen to them. Of course, whenever you increase these numbers, the pitch should go higher, okay? Play with these and you should see what I mean. Now, as opposed to these, okay, here you have just one sound, just one tone, one single tone, and here you have a combination of two tones. Here, now I'm defining a random signal, and you see rand is uniform, right? And I'm using this to produce 20,000 samples, but remember the function rand produces independent random variables, independent outcomes. Okay, all of these 20,000 outcomes are independent of each other. So what I have here is white noise. Okay, just display this and just execute this, and you will see, you will hear, in fact, what white noise sounds like, which you probably already know. I'm going to leave this to you. I'm going to conclude the discussion of white noise with this example. And here I'm describing what we call a moving average process. And again, this is very significant application. It's used in a lot of fields as a smoother filter, let's say. And the definition is you have white noise x of n, okay, whose variance at 0 is sigma squared. So that essentially Rx of tau is sigma squared when tau is 0. It's 0 otherwise. This is what this means. Okay? You have to be familiar with this representation. Now, you have this white noise, x of n, and we define y of n in terms of x of n. Okay? X of n plus alpha times x of n minus 1. Okay, so this is a random process that depends on x of n instantaneously, but also on its previous observation with the parameter, with the coefficient alpha here. Okay, so the autocorrelation of x is sigma square delta k, as I have indicated here. Okay, and obviously the power spectral density is sigma square. It's flat over all frequencies. Since this is a discrete time signal, the frequencies take values in 1/2. So this should be -1/2 up to +1/2. And the autocorrelation of y is by definition the expected value of yn times yn plus k. If you plug in the definition, yn is xn plus alpha times xn minus 1, and yn plus k is equal to xn plus k plus alpha times xn plus k minus 1. Okay, if you expand this expression, you will have xn times xn plus k, which is autocorrelation of x at lag of k, and then this one will give you alpha times autocorrelation at k minus 1, and these two will give you alpha times autocorrelation at k plus 1, and finally these two will give you alpha squared times autocorrelation at k, right? N minus 1, n plus 1, k minus 1, the lag is k. So essentially you have 1 plus alpha squared times the autocorrelation at lag k plus alpha times autocorrelation at k minus 1 plus alpha times autocorrelation at k plus 1. That's it, okay? And we know that autocorrelation of x is sigma square only when its lag is 0. So when k is 0, you see this will be 0, this will be 0, and this will be 1 plus alpha square times sigma square, which is the autocorrelation. Okay? And when k is minus 1, this will be 0, and this will be 0 because that will be autocorrelation at minus 2, which is 0. And this will be autocorrelation 0, which will be sigma square. So that will be alpha times sigma square. Similarly, when k is plus 1, then this will be 0. This will be also 0, but this one now will be alpha times sigma square. So when k is equal to either plus 1 or minus 1, the autocorrelation will be alpha times sigma square. And otherwise, any k value you put here, whenever k is greater than 2 in magnitude, okay, that means k is either 2 or more, or minus 2 or less, then none of these, k minus 1, and k plus 1, none of them will be 0, which means all of them, all of the terms here is going to be 0. Therefore, the autocorrelation is going to be 0. So this is something like 1 plus alpha square sigma square here, 1 plus alpha square sigma square, and I have alpha times sigma square here, alpha times sigma square here, and all zeros here. Okay, this is the autocorrelation of y, the process defined in this way. And when you have this autocorrelation, you can compute the PST of y by taking the Fourier transform of this autocorrelation. Just apply the definition. Here, of course, this autocorrelation is non-zero only for 3 terms, k equals minus 1, 0, or 1. So that is alpha times sigma square e to the power j2 pi f. This is for k equals minus 1. And 1 plus alpha square times sigma square times e to the power j2 pi f times 0. This is for k equals 0. And this term is for k equals 1. Okay, alpha times sigma square times e to the power minus j2 pi f times 1, essentially. And if you arrange this, what you get is going to be sigma square times 2 alpha cosine 2 pi f plus 1 plus alpha square. Essentially here, you should have used, again, the Euler identity to deal with these complex exponentials. But as you see, as expected, the PST turns out to be a real function.